All right. I don't know if my microphone was working, but check it out. I make the claim that these two, this is a simplified version for sure, but I don't think they're the same everywhere. What aren't we allowed to do? There's two things that we've seen that break stuff. And when I say break stuff, I mean specifically take us out of the real numbers. If I want a nice square root, the number has to be what? And I know we're not doing a square root, but so that's nice. What if I want a real square root? Doesn't have to be even. Like, does the square root of 3 exist? Now it's irrational, right? The decimal never stops, whatever. But is it a real number? It's not imaginary. So if we want to stay in the reals when we're thinking square roots, one of the things that breaks it, I have to have a non-negative. Now, I fixed Angel's language, or we disagreed a little bit. What's the difference between positive and non-negative? Zero is in the non-negatives. I can take the square root of 0. What else aren't we allowed to do? So I can't, louder. Ronaldo says we can't divide by 0. Now, in this first one, is there a value that if I chose it, it would make me divide by 0? In this form. Now, it divided out, but if we hadn't divided it out, what value of x makes me divide by 0? -1. Now, it would be 0 over 0 still, but do we say specifically you can't take a non-zero number divided by 0, or do we just say you can't divide by 0? You just can't, right? It doesn't matter what the numerator is. This function breaks at which x value? -1. So we're going to make a comment off the side between here, because we certainly want to simplify this, but we need to really stress that these two are not quite equivalent. So looking at it, I just want to check to see if my microphone is actually recording here or not. Can't tell. So between these two forms, we're going to make a couple really important comments. First thing, from here to here, we simplify, but not quite equivalently. And give me a just nice common layperson language. When we say it's not quite equivalent, what does equivalent really mean? The same, they're equal, right? So these are close. What we've really done here, and I'm going to wait till you guys catch up, is we've simplified. We haven't made something that's exactly equivalent, but it's really close to being equivalent. When we graph this and we get something that's not quite equivalent, this next statement is pretty abstract, but I want to make sure if this does not click, what's your job as a student? Like, ask. We can address this a bunch of different ways. I'm going to make one more comment in bright red so it stands out. We have a new function, which I know it's still called g. We could have called it a different function if we wanted, but we have a new function that agrees at every x value. Now let's say agrees with original at every, and I'm going to underline that, x value, except, and I'm going to let you guys catch up because we can either do this really general or in this very specific context. You're going to cut that out, right, Lando? Cool. Glad we're on the same page. Now, where's the 1x value that we don't agree between these two functions? -1. Now we have a choice to make. We can say, and I'm going to say we should say it differently than this, but I could say with every x value except x equals -1, and that's true. That's what broke it. But let's think of where that really came from. When I divided this out, is this a factor that we're dividing out? So how do you go from, if you're saying -1, how is that related to this factor? Good. It's the 0 of that factor. That's exactly what it is. It's what we get when we set it equal to 0, Sebastian. That was perfect. So we'll say we have a new function that agrees with the original at every x value except, and I'm going to put this because it's going to be kind of ugly, the root or the 0, the solution, however you want to word it, from the factor we divided out. Okay, this is very specific language. And I'm going to use this for divided out. We divided out a single factor, which means we agree at all but 1 point. What if we had had 2 factors that divided out? We would have a new function that agrees at everywhere except how many points? 2, and it would be just the zeros from that root, or sorry, the root from that factor, the 0 from that factor. Now, when we graph this, last little piece. We now have this, and I'm going to make one more comment. What was the only x value that didn't work for this function that we started with? So here's the huge takeaway. When this happens, when a factor divides out, when a factor divides out, our graph has a, and we're going to leave a cliffhanger here. I'm going to use the ellipses. I would not put ellipses on yours, but I just want to leave it so that we have a thought here. Okay, I'm going to pull up the graph on Desmos, and I want to see what happens and see if maybe there's something wonky about this. Who's better at graphing, do you think, you or Desmos? I disagree. Wholeheartedly, I disagree, and we're about to see why. It depends on the situation, just so you know. Okay, now, first thing, because I said cliffhanger, did you guys see the Alex Honnold thing the other day? Do you know who Alex Honnold is? So the dude is insane. He's a free climber, which if you don't know this, he does rock climbing without any ropes. If you guys have ever seen Yosemite, like Yosemite National Park, El Cap is like one of the huge achievements that a rock climber can make. He climbed it without any ropes years ago, and it made the most uncomfortable 90-minute documentary. He did a live show the other day where he climbed. You know how tall it was? Like 100-story building in Taiwan with no ropes or anything, and people just cheering the whole time. All I could think is, it just takes one person in the inside being a jerk to try to startle him. And nobody did, thankfully. But anyway, speaking of cliffhangers, we're here. Okay, let's look at the graph of these things. Yeah, dude's crazy. I'm going to go back so we don't see that graph there yet. And let's check it out. Okay, we have two functions. We have f of x, which is 2x plus 1. I'm going to move this out here. Okay, what is my other function originally, my g of x? Okay, I want you guys to help me discern the differences here. Here's f, it's the red one. Here's g, it's the blue one. Isn't there? Okay, so you're right. Seemingly the only difference is the color that I've chosen, right? But I'm lying to you. Where did the weirdness happen? So let's just turn on just the blue one. At -1, there's supposed to be something strange happening. And we just haven't commented on what it actually is. Do you guys see anything strange happening at -1 right here? So maybe if I just zoom in a little bit. Here's -1 still. Anything strange happening? Maybe not. Here's where we're better. Now, we know that that function does not work at -1. Do we all agree with that? It can't work at -1. Well, we need a way around this. We're going to go back to an old school geometry. What's a point? Like, not on your page. A point on your page is just a dot you draw, right? What is a point, though? A coordinate. I agree. Can we be more specific than that? Or maybe maybe. I was hoping you were going to use that word in your answer. So like right now, we're in 3-dimensional space, I think. Okay, this is a challenge. And we're going to see if you guys can do this real quick, but I promise it ties in. Hold your hand out. Do you agree that at the tip of your finger, there's a point right here? Yeah. Like in 3-dimensional space, here's my challenge. Can you look at that point on the tip of your finger? Like it's just, imagine it's there. It's just barely in front of your finger, right? So you're looking at just the tip of your finger. Now here's the challenge. Everybody's focus is right here, like a foot away from your eyes, right? Take your finger away. Can you keep looking at that point in space? It makes my eyes kind of go cross, is what it does with my eyes. And when I try to still look at that spot in the air, like my focus just doesn't work. There's something wonky happening. How big is a point? Back to geometry idea. Small. How small? Fairly small, or like, oh my gosh, infinitesimally small, which just means infinite but with decimals. Like as small as you can get, because a point is literally just a location. If you guys think back to us solving systems earlier in the year, I said I hate solving them by graphing, it's because our points don't do a good job. 2 looks like 2.01, looks like 2.001. We can't really see it because we have to actually draw it, right? Now, there's something going on here. We know something wonky happens at -1. Your calculator will give us the same graph. I'm really zoomed in right now. If you can't tell, here's -1. I'm going to drag along the graph, and we're going to see something very familiar. I'm getting really close to 1. I'm at -0.99. 995, and we're going to go right to that point. And what happens for one brief instant? It's undefined, and how does it represent it as soon as I hover over it? What changes about the graph? And I'm going to make this like obnoxiously large if possible. Let's see if I can do this. I don't know if I can. I should have done GeoGebra. Let me see if I can make like a thicker line here. So we'll change this. Oh yeah, 2.5 is what it was. Let's do like obnoxious. Okay, I'm gonna get closer and closer to -1 again, and you guys tell me, what do you see happen there? And how did they represent it on my graph? A what? A open dot. It's like there's a hole right in the middle of my graph. But if it's at a single point, we're never gonna be able to see it, because how big is a hole or a point? Infinitely small. Like you just can't even point it out. It's just a single location, which means when a factor divides out, our graph has a what? An infinitely small point that it doesn't touch. We're going to refine that as a hole. Just with our open circle, our graph just happens to have a hole, which means when we compare these graphs, and I'm just going to copy and paste this one, I'll just change it because I know they look exactly the same with one exception. If this is our graph here, we have a hole where? At -1. So would you guys believe that if that's +1, -1's about right here? So I'm just going to go to that point on the graph, and I'm going to erase it. And here's where I legitimately believe that you're better than Desmos. Can you guys see the hole on this graph? No. Can you see the hole on our graph? We are better at graphing this situation. Your calculator, you won't see the hole. You can't. Because it's infinitely small, you won't see it. But we know it's there because we had a factor that divided out. This is going to change a lot of our graphs in a good way. It makes it easier to graph because would you rather do the vertical asymptotes, horizontal asymptotes, and all that good stuff? Would you rather just graph the linear function here? Awesome. Seems reasonable, seems super hard. Reasonable. So last little thing, we are asked to graph it. That's fine and dandy. That was one of our big ideas. The graphs, what's the major difference between them? One has a hole. That's our contrasting thought. And then last little part, I'm going to call this one g, so it's the right function. That's g of x now because we graphed that similar function. What is the domain of this wonderful function g of x? It's every number with the exception of 1. And that was unintentional that it was about the same number. X such that what x cannot be? It can be 1. It can't be -1 because it would have made our original divide by 0, which makes it so that we have a hole in this one. X can be any number except -1. And we have our domain from our graph. Now, as we go through, we can make these uglier. Whether it happens necessarily this year or not, we'll see. But let's do one more. And by let's, I mean I want you guys to do one more. Before I just cut you loose and give you a head start on it, I want you to turn and talk with your neighbors. I'm going to give you 30 seconds. Which part of this did not just click? That's my main focus right now. I need to know, where did I lose understanding? 30 seconds, talk it out. Kennedy, we're going to break it down. Let's hit it. You got some good questions. Let's hear them. Do you see what we divided out? If you set that equal to 0 to get its root, what would you get for x? Yep, it's whatever factor came out, the root associated with it is what we're going to put the whole. So then what do you do with that? So I note it, like we made that comment off to the side. On my graph, it shows up as a hole, so I know that I missed it. Like it is all there. We just omit it or get rid of it from the domain. That's it. So when we go from the domain that was all real numbers, we said, hey, this is the exact same, except for this one place that made me divide by 0. And so it'll take a little bit of practice. If it divides out, whatever that factor thing is, set it equal to 0, and there's your hole at that x value. And we'll get practice. Okay, so one of the questions is, where does -1 come from? Which is a good, reasonable question. How did I get -1 from this? So I agree, but this says x plus 1. Why did it turn to -1? So I like both those answers. I set it equal to 0 and I get -1. That's the scratch work that we don't see happening. Now, I want you guys to do one more for me, and feeling, we'll just go like class vote. Thumbs up says, yeah, I just want to try this with my neighbor. Thumbs down says, I want to try it, but I need your help, Holloway. Where are you guys at? Okay, so I see a few people straight down. I will be around to work with you like individually as you have questions. I'll just be walking around, and it's your job to do what when I walk by you? Yeah, to ask. I'm not gonna, yeah, I don't know what I'm not gonna do, but let's do one more. So we'll call this example. Let's see if I need a new name. I do. So right off the bat, we're gonna bounce back and forth between examples and such. Let's actually start here. Our first big idea that we're really covering now in 4.3 is what happens when these things divide out. So dividing out factors is what we'll call this first little section. So we're seeing what happens when we divide out. We want to make sure that we don't lose all those ideas related to graphing and things. And our subsection here within dividing out factors is simply going to be holes in graphs. Now, we already have this statement written above, and I want you to verify that you can find it in your notes. We can write the same thing here if it would help. I would encourage that if you're struggling, I would suggest you do it. But up above, we said when a hole happens in a graph. It was up here on the right next to those non-equivalent expressions. What did we say? Holes appear when what? Or where? So what points? So I agree with that, but look up, what did we say? How do we know that there was a hole in the previous graph? We wrote a comment right up here next to this graph. I think I wrote it in pink, but I'm trying to not just scroll up. The root from the factor that did what? Divided out. Do we need to write a graph will have a hole at the x value at the root of the factor that divides out, or can we just keep it from above? One more time. So whatever factor divides out, we just set it equal to 0. And that's it. So we can get some nice ones. We can get some ugly ones. Let's try one out and just see how it goes. So example, I want us for these first ones, all we're going to do is simplify and find domain. And find domain. And I'm not going to make us graph these unless you guys are just dying to do that. But here's our first problem. Let's jump in. On A, I want us to deal with the following lovely function. And I'm going to go ahead and do some numbers just so we can talk about it. We'll say this is equation 1. It's our original, just so we can keep it straight as we're discussing. And I want us to deal with the following. We have x squared plus 4x plus 3. And I don't know why I didn't say this. It's going to bug me. Equals f of x. That annoys the crap out of me, but we'll be okay. Okay. We're going to simplify this thing. We're going to find the domain. And I think that I lied to you. I do want to sketch it, but we'll sketch it together. And sketch. So for the first part, this is going to drive me crazy. Just so you know, I am going to change it because it's already just, can't stop thinking about it. I want us to take this function and divide it by, I don't know, how gross do we want to make it? Okay, super gross. You got it. Let's do x squared minus 1. This whole thing is equation 1, and I'm going to fix it because, again, it's just driving me crazy. I'm just going to call it f of x still. I'll still call it equation 1, but yeah, whatever. That's equation 1. I want you guys, step 1, factor it. Factor everything. Factor the top, factor the bottom. Let's see if we can find that equivalent form. Appreciate you getting down here so quickly, by the way. So I appreciate you getting down here so quickly. And no problem so far. It's been working, like, flowing smoothly. Yeah. So here in a minute, I'm just gonna refer to this as equation 1, and then our simplified version we'll call equation 2, so that we don't have to say. These aren't part of the equation. Nope, that's just so we can talk about it. Okay. The 1 there, guys, just to be super clear, is because we have this version. You're gonna give me a factored version as well. I'm gonna call it equation 2, just so we can talk about it. Cool. So your job right now is factor the top, factor the bottom. Factoring stuff still a little rusty. All right, so I'm gonna grab you something real quick. And RJ, I might have given you one of these at some point, but I might not have. Have I given you one of these? Okay, I'm gonna let you use it still. Okay, so that's fine, but let's check it out. So this one's, I'll try to make a nicer one that's not quite as ugly. Are you cool with factoring? All right, factor the top and bottom for me, and then we'll check. Anybody else feel like you struggle with factoring? I will make a nicer one for you, but I do have this. I gave you one? Okay. If you want to see what I'm giving out, this is a pre-calc thing that I made last year. I'm going to make a nicer one for algebrists. Yep, I got you guys. Okay. So looking at this, let's just run through. For those of you that I just gave one of these bad boys to, all good? Perfect. I do. Yep, I have the key. Thank you. Okay. I will make a nicer one. This is a factoring guide that I have. I can get you guys copies of it if you'd like. Those of you that just raised your hands, I gave you some. Looking at this, just to show you guys what we're looking at here. If you don't have these in your head yet, I hope you do. But if you don't, I do have a way to help you kind of keep it straight. First thing we always check with factoring. GCF. Okay. So just as I pull this up, here's this big ugly thing. It says, you give me a polynomial, and it's ugly. Right away, as we just run down this, and again, I'll hook you guys up if you want one, it says, does it have a GCF? If it does, factor it out, right? We always do that. So we'll just bounce back and forth. Is there a GCF in the numerator? No, it's just one, right? So now we keep kicking. Is the numerator is all I'm looking at? Is it a binomial? No, so we keep kicking. If it's not a binomial, I don't worry about the difference of squares or cubes or the sum. Is it written in a quadratic form? So I know this is ugly where it says 2 to the 2n, but I don't care if it's really a quadratic because this could be 6 and 3 and it still works because I can write it like a quadratic. Okay, once it's there, this order, it's not always the way we go. Is it a perfect square trinomial? Which can be hard. Maybe you guys remember talking about them, but the real question is the middle term the product of the square root of the first and the last, or twice that? So I don't know the square root of 3. It's not that. What's next on our list? Is the leading coefficient 1? Hey, can you find factors a times c from this thing, a times c, that add up to this middle term b? Yeah. What's a times c give me? 3 and 2 factors that add up to 4? So check it out. We're going to write the second version then. This version of f of x is slightly different. We said it was 3 and 1, right? X plus 3 and x plus 1. Okay. How about the denominator? And I don't like the way that one looks. X plus 1, x minus 1. And I'm going to change the order here. How did you know that? So let me rephrase that question because there's a lot of ways you could answer it. What type of factoring did Angel just use? Difference of squares. Cool. So here we are. We have it factored at this point. Is there anything that you guys see can happen? These divide out, right? Okay. Now, when they divide out, we're going to do some work off to the side just because this is the most common question. I divide them out. Yes. I heard Mr. Holloway, but I don't know who said it. This is our whole. So check it out. This little crossing out right here tells me that there is a whole in graph. And we're going to be more specific than we were on the previous, just for this one. When x plus 1, the factor that we just divided out, is equal to what? 0, which is really when, and I'm just going to say one more step, there's a whole where? At x equals -1. So when we draw whatever graph it is, all we do is we go to -1 and we just put an open circle to say, look at this, there's a hole in my graph. Okay. Not to call anybody out, bless you. Kennedy, you had a question about this. Does this statement help clarify? The factor that divided out was x plus 1, and I just set it equal to 0, and that's how I got where my hole is. Cool with that? Love it. Okay, so now, do we have a simplified but not quite equivalent form? So I'm just going to rewrite it with everything nicely written so we don't have any ugly stuff. X plus 3 over x minus 1. This is what I'm going to refer to as equation 2. It's not our just factored form anymore, but it's our truly simplified form. Okay, original, factored, simplified. Okay, same, almost the same. everywhere except one spot. Now, as we look at these, we want to find the domain and to sketch this function. Now, this thing is a little bit uglier than the one that we did a minute ago, I think, because this is not just a straight line. This is a hyperbola, which if you don't remember, it's these things, those wonky things, however they wind up looking. So we now have to graph this, but we don't want to lose it. There's a hole in it. So if I want to graph a rational function, there's like 4 things that I ask you guys to find when doing that. Can you give me one of them, Fred? Yeah, if I want to graph this, there's 4 things that I asked you guys to find on the quiz the other day, but it's exactly what we need to graph these. Any of the 4? Like, are there any places where there's a line that I'm not going to touch or that I'm going to get arbitrarily close to? Vertical asymptotes. Where do we find vertical asymptotes? Love it. Julia is confidently whispering here the zeros of the denominator. Now, in this simplified form, my denominator is x minus 1. Lando, what makes this denominator 0? I like that more. There's a vertical asymptote at x equals 1. And the way that Lando got that in his head, and I'm just going to put it in pink here so it's just like to show, is he set this x minus 1, the denominator, equal to 0. Awesome. Nice job, Lando. What else might we have? And check it out. We're going to do this. Mark. I need vertical asymptotes. What else do I need, Mark? It's weird, right? Say it again. Horizontal asymptotes. Okay, cool. Horizontal asymptotes. And I'm going to go back to this. And I'm going to make one more little comment on this here in a second. How do you find horizontal asymptotes? So we have to compare the somethings about the numerator and denominator. So before you just jump to leading coefficient, and I love that that's where your heads are, we got to check something first. We only use the ratio of the leading coefficients if what is true about the degrees. They're the same. Now, what I'm going to add to this here in just a second is from this one, did we look at version 2 or did we look at version 1 to get our vertical asymptote? So I'm just going to say equation 2, and I'll just write it here so that we can reference it. I'm just going to write it exactly like this. This was equation 2, hence why I numbered them here. What do we use to get our horizontal asymptote? Are you looking at equation 1 or equation 2? Can we look at either? I think so. What's the degree of the numerator here? And here? They're equal. Leading coefficient over leading coefficient is 1. What's the degree of the numerator now in our simplified form? And here? And 1 over 1 is? It doesn't matter which one we look at for this. I will typically default here because if I have some uglier factors, it's easier to find those numbers. But where's our horizontal asymptote then? Y equals 1. Now, 1 or 2 works for this one. Doesn't matter which equation we use. Say 1 or 2. What else might I need to graph this? Hey, I need some x-intercepts. Now, to find the x-intercepts, and I always write them as ordered pairs, just so that we don't get it confused with our asymptotes. How do you find the x-intercepts? The zeros of the numerator. Do you want me to do it from equation 1 or equation 2? 2 is definitely the way to go. This is an equation 2, our simplified form. And what value of x makes my numerator 0? -3. So how should I write it if I'm trying to write it as an x-intercept? I might have ruined it because I wrote my parentheses first. -3, 0. And real quick, we'll just make the note. We just set the numerator, which was x plus 3 equal to 0. And I'll add this one in case you need. Y equals leading coefficient of n over the leading coefficient of d. Anything else that we would use to graph this? Any other information that you would like to have to be able to graph it? They might need a couple points. We can make the points now, or we can make the points on the graph when we decide we need them. Let's make the points on the graph when we decide we need them. Because everybody struggles with this part. I legitimately believe, and honest opinion, that this is the harder part of the problem. The actual graphing, it's the easiest part for me, and I want it to be the easiest part for you also. Okay, so I'm going to draw a scale, and I'm going to think it out just a little bit. I know that I have to see x equals 1 and y equals 1, so I'm thinking positive and positive. Sorry, from your perspective, positive x and positive y. What's the furthest left my graph ever needs to go? -3, so how far should I go if I need to be able to see -3? Maybe -6, -5, somewhere in that range. Can I just do, I don't know, what scale do you want? Let's pick it. So here it is, and we're just sketching this thing. More right or more left? Based on all this. More left probably a little bit. And it doesn't have to be perfect, but maybe I don't need everything to the right. So we have a lovely x-axis and a lovely y-axis. I'm going to give you guys like 60 seconds. I want you to put on the information that we already have, and we'll come back together and see if we can't logic it out to just get ourselves a nice sketch of this function. Asymptotes, points, if you're feeling ambitious and you want to graph it, feel free. I think that's awesome. But we'll graph it together here in just a moment. I'm going to be real nosy and look over your shoulders to see what you're trying to do. How do we draw asymptotes? You dash them. Love it. You can also grab colored pencils and use those if you'd rather. Yo. Another day, another dollar. Hey, did you get the up dog I left? Yeah. Not much. What's up with you? Got him! That's the first time that's ever worked for me. No, that's exactly how you do it. All right, what are you thinking? Where you at?
I'm thinking like
So I would pick a little bit bigger scale. Like I know that it's natural to want to use these little squares, right? But do you agree? Like I'm old, so it's hard to see. Can we jump? If we only need to go to -3, can we just jump by like 2 maybe?
-2.
Because I see that there's a -3 that we're gonna have to see. So I would probably just go, and I would put your marks -1, -2, -3, -4, and I'm fine with that. And so we'll catch up with this. All right. So looking at this, here's my lovely graph. I have not picked the scale yet. Do you want me to jump by ones, twos, threes? By ones? I would not normally, but I'm okay with that. So let's see. I need to go out to -3, right? So maybe I'll start here. Somebody said -6. I'm cool with it. And I know you said ones, and I'll switch it to ones. I'll put those tallies. If that's -6, this must be -3. And then each one of those, even if I don't put the numbers, is it reasonable to say that we can probably find those numbers? Okay, if that's -3, then +3 about here. Okay, now if we're just sketching, we can pick a Y scale. We're gonna have to get a little bit more information, but if all we're after is just a general shape, maybe we don't truly need that Y scale super hardcore. What else should I have? Asymptotes. Okay, where do I put a vertical? I'm gonna just use a pink line on mine. Through 1. Okay, so here it is. X equals 1. Now I'm not gonna dash mine. You guys should, unless you're using colors. If you're using colored stuff, I don't care if you dash it or not. Okay, the other thing I want you to double check for me. If you're not dashing, you're just saying, Holloway, that's stupid, I'm not going to do it. That's your right. I'm not going to make you write it the way I do. But do you have your axes labeled? Because if you don't, when you start adding a bunch more horizontal and vertical lines on your graph, good luck keeping it straight. I would have the X, I would have the Y. Okay, there's that one and a horizontal asymptote. Now I have to decide, should we just keep the scale roughly square? And do you know what I mean when I say, should we keep the scale square? Okay, so I got a lot of people said yes, but fair. This is how far 1 is, right? So if I want it square, this is how far 1 should be. I'm just making it so it's square units. There's 1, there's 2, which means there's 3. Okay, I have a horizontal asymptote right here, almost right here. One of these things I can't touch. Which one? The vertical. Might I touch the horizontal? Yeah, because the horizontal is not really and truly an asymptote. It only tells me about how the function behaves where. Ooh, the horizontal, I heard somebody else say it over here, though. End. The end behavior is all it's telling me. So we have those. Okay, done. What else should I do? The x-intercept. Nice. It's at -3. It's right here. Now, I think that I have enough to graph this. Like, legitimately, I do. Could we get a little bit more information if you're not comfortable graphing this function? What are some easy values we might plug in? And I'm going to use equation 2. So I'm going to make a note here. Use equation 2 to get a few extra points if you want. to get a few points. Now, you could use either because they agree at everywhere except a single point, right? Why would I prefer equation 2 over equation 1? Oh my gosh, it's so much simpler, right? Like, we're going to get the same numbers. Let's just use a simpler version. So all you guys have to help me do is I'm going to write f of, and then you're going to help me get some x values that you want to check. And I'm just going to copy this so I can just do it over and over. What's the first x value that you might want to use? 1 won't work because it's undefined here. 0 is my first thought. If I plug in a 0 for all the x's, here they are. What do I get? I get negative 3 over negative 1. Do we agree it's negative 3? So check it out. Once I do that, I'm just going to eyeball it about there. I now have that point. I'm even more convinced that I know what this graph does. Okay. It definitely has to go downward, and I can see that. Now, I knew that before because check this out. How many places does this graph cross the x-intercept? Once, and it's right here. There's never going to be another place it happens, right? Which means in my head, and I know it seems weird, but I'm actually going to think about this other side. On the right side of this graph, I have two options. We have this option that gets really close like this and does something like this. We'll call this option A just for conversational purposes. Or we have this one that we'll call option B for conversational purposes. I know it can only be one of these two. Here's what we're going to do. You're going to rock, paper, scissors. One time, we're going to see who wins, and you're going to describe, whoever wins gets to pick if you're listening or talking, describe how you know which choice it is. So one quick round of rock, paper, scissors. Winner chooses whether you're describing or listening. Good. You're doing one game of rock, paper, scissors, and whoever wins, and I'll show you. Just go ahead. Okay, so you won. Do you want to speak or do you want to listen? Okay, so Lando, your job's to listen, your job's to speak. How do you know which one it is and why? Whether it's part A or B on this other side. Yes, ma'am. So check it out. How many times does it cross the x-intercept? Which one crosses it a second time, but it's not allowed? A or B? B's garbage. It won't work. It can't work. That's it. That's all I'm after. Can I call on you? Okay. All right. So we have about 30 seconds. We're going to clean it up. Perscovia said something I really liked. She said it has to be A. Why? B would cross the x-axis again. And I know it doesn't because there's only one root, which means the last thing that you do before you leave class is we're going to graph it. I know over here it passes through these points. And I'm going to miss it, but that's okay. There's our first one. And A or B it had to be? Has to be A. And that's really misleading the way I worded that. I'm sorry. Cool. Tomorrow, bring your algebra hats. We're going to be doing a bunch more of this. Well, you better make one. Learn to sew. All right, peace out, Raiders.